We'll go over this multiple choice test. All right, so first of all, the first one says, all things being equal, larger automobiles has less fuel efficiency. It also says they're trying to see if there's the effect of engine size on the fuel efficiency. Now that's worded a little bit weird, but they're trying to see what effect does this have on this part of it. So that makes the response variable the fuel efficiency and the explanatory the size of the engine. That's not super obvious on that one. All right, so then it says gas mileage is the response variable and you would have a negative association. I'm definitely liking that one. I'm always cautious of A being the right answer, so let's go through the other ones. The gas mileage response variable, check. You would expect to find a positive? No, not positive association. Gas mileage is the explanatory variable. That's wrong. And you would expect to find a strong negative. So, I mean, that one's pretty close, but that I needed to identify the explanatory and response. Not just by saying which one's on the X and which one's on the Y, but more of the independent, dependent. That's pretty crazy. I mean, kind of a difficult problem. In gas mileage explanatory, you'd expect very little association. I mean, here's the deal. It's possible that this could be the right answer on another problem, but there's no way you can make the argument that there wouldn't be a relationship by how big an engine is and how much fuel it takes up. So that one's out because I disagree with the very little association. All right, next one. The next one, they give us the equation. They do use the y hat and x and then tell us what x and y are. In an FRQ, you'd have to define x and y a little bit cleaner than that, which is why we don't write the equations. But basically, they say they use the first test x to predict the score on the second test. And that seems reasonable. So the first one said 95 for the first test. So I went ahead and multiplied the first two things out here. But if I plug in 95 in for x, I get 95.5. And so there's my answer D. I just went ahead, saved a little time, had that typed in already. And the next one also. So in the next one, using the same thing in number 2, Bill got 90 on his first test, and then he scored 93 on the final. What was the residual? So that's a little bit heavier of a problem. So again, I go into the calculator, I plug in 90 for x, and I get that the expected or predicted score was 91. Okay, he got 93. So he did better than what we expected. Better than expected means positive 2. And again, notice they give us -2 to throw us off. The other ones, they don't give us like 3 and -3, but they give us 2 and -2. And that's, again, and forget the formula. We got more than expected, positive. All right, the next one, you can read this, and hopefully you tried this on your own first, but bunch of reading, and what they're doing is they're converting units, okay? But they're asking us then what happens to R. And the answer is nothing. Nothing has happened to R because R has no units. So you can change units all day long. It doesn't affect R at all. All right, the next one. The next one is one of those where there's 5 true and false questions, and these are always a challenge. All but one of them has an error. So one is true, the other ones are false. The correlation, there is a correlation of 0.5 between a position of a football player that they play and the weight. Okay, now, I won't talk about this very much, but for Unit 3, for all this prediction business, you have to have quantitative variables, not categorical. So in this problem, the position of football players is categorical. Therefore, there is no such thing as a correlation between these two. Part B, we found a correlation between -0.63 between gender and political party preference. That's 2 categoricals. That's even more wrong or wronger than A. So that's definitely not good. But we didn't talk about that a lot. So those are some connections that, I mean, I guess if you're watching the video, you won't have to make, but there you go. So it has to be quantitative variables. So the next one, the correlation between the distance traveled by a hiker and time spent hiking, so those are both quantitative, so that sounds pretty good, is R equals 0.9 meters per second. R has no units, so that doesn't make any sense. And I obviously already crossed this one out, didn't have the perfectly clean formula, multiple choice test here, but we found a correlation. Actually, it's not even that. It's this part right here. No, R is fixed between -1 and 1, inclusive. It can't be greater than that. So by process of elimination, E is the winner. But the correlation between mid-August soil moisture and the per acre yield. Okay, per acre yield is how many tomatoes you got per acre. Farmer is going to have several hundred or several thousand acres, but per acre yield, that is definitely quantitative. This one you could maybe make an argument for both ways, but since the other ones are out, for sure, this one they actually have a soil moisture, value by numbers. All right. Oops. Okay, the next one, something happened to the hat, and that's what's going on. That should just be Y hat. Hopefully that was obvious, but if not, there's your explanation. So it says the set of data describes the relationship between the size, the annual salary raises, and the performance ratings. So again, we would expect that to have a positive outcome. This shouldn't be too crazy. So here we go. Which of the following must be true? So again, one true and the rest of them are false. For each 1 point increase in performance rating, the raise will increase on average by 1,400. Nope, that's the y-intercept, not the slope. This sounds like the slope, but it's the y-intercept, so no thanks. The actual relationship between salaries and performance rating is linear. The actual relationship between salary raises and performance. So on this one, we can't tell that it is linear. We got an equation for it, but we don't have any proof that it is actually linear. They don't even give us the R. That one, they're even getting a little bit trickier on that one. But we would have to be able to see the residual spot. So it might be and it might not be. You can still get the equation, but man, that's a mean one. The residents for half of the observations will test positive. Like, what are you even talking about? Like, you say, what's wrong with that statement? There's nothing right about that statement. The correlation between salary raise and performance rating is negative. Nope, it's positive. That one's easy. A mean performance of 1.2, the mean raise would be 3,800. So I did not pre-type this one in, but we're going to plug that in the formula and see what happens. Oops. Bingo. That one is correct. Now, they're trying to talk about the mean instead, but remember, mean is a measurement in a center, and it is affected by multiplication and addition, so we just plugged that one in. If that would have been something in the standard deviation family, I would have just multiplied it by 2,000. That would have been a much meaner question. The least squared regression line for, again, blah, 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 residual plot. Look at that. That is a clear pattern. That is not linear. You don't have to say the entire thing, which you will on your FRQ, but if you knew that thing that you had to remember, and even if you saw this in May, you would know that the curve pattern says a linear model is not appropriate. So there we go. Also, by the way, sometimes they call this the high, low, high, and if it went the other way, it would be the low, high, low, but again, haven't talked about that in class, but there's an extra nugget for watching the video here. All right, the next one is asking about the least squared regression line definition, basically. But the least squared regression line, so least squared, minimizing the sum of the squared residuals, that's what we're trying to do. Definitely the squared. So this one doesn't say squared. This one doesn't say squared. And then minimizes the particular, nope, doesn't say, it's the square, I guess least squared regression line. So this is a perfect example of, I wouldn't really expect anybody else to get better than 50-50 on this one. But you should, again, least squared regression line, I think minimizing the sum of the squared residuals, I think you should be able to get that. And then this one is because it's the correct answer is it minimizes the sum of the squared residuals between the actual yield and the predicted, instead of the actual UV versus the UV. UV is the X. We're doing, when we do the residual lines, remember we're always measuring the distance from the dot to the line. That's going to be the Y distance, so we'd want B. But 50-50, I'll take it. That's probably the hardest question we've had multiple choice yet. And you should have been able to get to a 50-50 on that one. Next one, which of the following is correct? And this one is an interpretation of the slope. So it should be for every increase of 1x, we expect a decrease to the y. And on this one, it's UV measured in Dobson units. And then at the end of the experiment, the yield kilograms was measured. So kilograms is your y. And I'm just going to cheat. It's the answer C. If the UV is increased by 1, okay, if x is increased by 1, we expect, now they use expect instead of predict, but that's why I say both of those, a decrease of 0.04. And there it is. All right. The next thing, which of the statements, again, this is III. We don't love these either, but this is good practice. Which statement below about the least squared regression lines are correct? So again, true and false times 3. And they want to know which ones are correct. Switching the explanatory and response variables will not change the least squared regression line. That's a big no. It will not change the correlation so that's R or R squared, but that's not what this is. The slope of the line is very sensitive to outliers in the x direction with large residuals. I don't want to get into this too much, but just the large residuals part of it. You got outliers with large residuals. What's that going to do? That's going to make this maybe a 0.9. And here, now it's going to be maybe like 0.6 or something. So very sensitive. That's another way of saying it, I suppose. But I'm saying that's a yes to number 2. The value of R squared is close to 1 does not guarantee a relationship between the variables is linear. And oh my gosh, you better know that one. Because the only way we can say a linear model is appropriate is if the residual plot, etc. I'm not even going to say it. I'm starting to cut down time on this one. All right, so there's the first one. The next one, a lot of the questions are very similar. So again, what's the predicted? What's the residual? With this equation here instead. Don't have this one plugged in, but again, it's not that big of a deal. 64.93, and plug it in just like it is, except in place of x, we're going to put parentheses, whatever they give us. I think that's why they actually like it in this format. You just plug that in. 79.105. That's say, oh, why did they round it to? It doesn't matter. It clearly is that answer. All right, the next one, and by the way, if you hit second enter, you get exactly what you typed in. And so now I just need to change this to 20. Oops, 20. Delete. It's a little bit better than typing them in. Okay, 77.53. But that's not my answer, so I'm going to even get rid of that one. That's what expected. I got 80 centimeters. I expected 77.53. I got about 2.5 more than I expected. So right there, the actual minus the predicted, more than expected positive. Next, number 3, you have data from many families on parents' home and income and years of education. The eldest child completes. Your initial examination data indicates that the children from wealthier families tend to go to school longer. When would you make a scatter plot? When would you make a scatter plot? Oh, what would happen? Not when would you make it, but when you make it, what do you expect? So first of all, it says since it's the more means longer, positive. So negative is out and negative is out. So we have, we got 3 left. Very little association. Well, it just says it indicates that that happens. So very little association would mean 0, means not much positive, not much negative, close to 0. So then we got 2 of them that to choose from, and it's the explanatory. So again, which one was the X, which one was the Y? So what we did on this problem is we looked to see how much money they had. Okay, and here, let's just go back. You have income and the years of their education. Your initial examination is to indicate that children from wealthier families tend to go to school for longer. So they said they looked at the money and then that had the effect on when they went to school. It's actually kind of confusing right there. I'm not going to lie to you, but that makes this B because the explanatory would be the income and the response variable would be how long they went to college. Okay, number 4. I think this one's pretty funny. It just talks about some stuff, and it says, hey, the statistician came up with this value for correlation, and then, yeah, that doesn't even make sense. So if the statistician comes up with this number, they clearly don't know what they're talking about. But that seems like a little bit jokish for a problem. I don't think we'd necessarily pick one like that on the test. But if again, maybe you should figure that one out. The next one, agricultural economist says that the correlation between corn prices and soybean prices is R equals 0.7. That means that when corn prices are above average, soybean prices tend to be above average. As one is big, the other one is also big. I'm liking that one. But again, I'm going to be careful about any choice A, or let's find out why the other ones are wrong. There is almost no relation. False. 0.7 is way too big for there to be no relation. Corn prices are above. The other ones are below. That would be negative. Soybean prices go up by $1. These go up by 70 cents. Good try. That slope, I would understand if you pick that one. You're just thinking of slope. You just don't remember R's correlation. The economist is confused because correlation makes no sense in this situation. And that's that categorical versus quantitative, but this is prices in dollars. So A, as it happens, is the correct answer. Which of the following statements is true? This IIII, including a bonus one here. This is true. Every least squared regression line goes through. If I find the mean of X and the mean of Y, and I plot that point on the graph, that line of best fit will go through it no matter what. I don't believe we covered that. But there's a video bonus, I guess we'll call it. The correlation requires that correlation requires that there's clearly identified explanatory and response variables. That seems like it's right, but it isn't. I could just give you the values of all of these points, 20, 30. We'll call it 20, 3 because I already got it. We could say this is 30, 2.9. And we could do correlation. We could do that math. We do not need clearly defined. Now, for a write-up, we need to include that context, yes. But that one is no. And it sounds good, though. It sounds good. Scatter plots require both variables be quantitative. That's a yes. If you listen to the first part of the video, we have talked about it. That's, again, one of those things we really didn't talk about in class. There's an approximate linear relationship between the height of females, given the ages, and with this equation, the height, and that should be hat. I'm not really sure what's happening there. I tried to fix it, but there was no fixing it, and I quit trying to mess with it. And then they give us the equation where it says height is measured in centimeters and age in years. Which one of the following must be true? An estimated slope of 6.1 implies that the child grows between the ages of 5 and 18 by about 6.1 centimeters for each year they grow older. That sounds really good. That's interpreting the slope in a multiple choice. Again, but let's be careful, or again, let's go. That is correct. I'm just going to spill the beans, but let's go over these real quick. The correlation between height and no, not negative. The estimated intercept is 50.3. We conclude that the typical height of a female at birth is 50.3. No, I like that one very much, but it said from age 5. So the y-intercept is the height at age 5. That is mean, though. That is a mean answer. The heights of 68% of the female children who are 10 and older within 6.1 centimeters of 110. Like, what are they talking about? I mean, I guess you could plug it in and get that number, but like, what's going on? This doesn't make any sense. And again, what's wrong with that statement? It's like nothing's right with that statement. My niece is 8 years old and is 115 centimeters tall. She is shorter than average. So what we would need to do is we would need to see what the expected score was, and here. So 8 times 6.1, and then plus the 50.3. That's what I'm just adding them in, not typing in. And this is expected. She is taller. That's a no-go. Choice A. All right. Number 8 is basically asking you to find least squared. what does least squared mean? And this is actually a little bit easier than the one that was, I hated that problem. This one, number 8 on this one from the computer output, that was the complete, plus they made you do the units. This one is just minimizing the square root of the residuals. You can read through those. I really don't want to spend much time on that. Okay, next one, look at that. That is a residual plot that has a clear pattern. Guess what? That ain't linear. D. And I'm gonna confirm with my paper on the side that I didn't pick the wrong one for some dumb reason, didn't read it careful, but I mean, again, let's get it when we see that. All right, next one. Right here, there. You know what? You can read this, but and I'm tired. I'm tired of doing this. But and we got our output. We do have a positive slope, so I don't have to worry if they're messing with us with R. This one also, see, sometimes they don't give us all the same information. They do give us R squared, but that's a no. And also remember, these are a no for right now. So normally there's a S also, but this one, they're not even trying to trick us with doing S. But we do need to know which ones we're not using. There's the slope, there's the y-intercept, and there's R squared. All right, which of the following is true? If one of the students in the sample had a height of 70 inches and an arm span of 68 inches, then the residual for this student would be negative 2.36. All right, well, let's check that one out. So again, remember, this is height, and height is the x. So we got 11.5474. And it's multiple choice, so I don't have to make it perfect. I don't have to make it perfect. And then times the height. And on this one, it said height of 70, so they're being nice. Okay, well, kind of. They're making us calculate residual on a multiple choice problem. It's not that nice. But and there's a few decimal places in that one. I have done something stupid. Wait, and 70 is... Oh, goodness. The height, the arm span is 68. Well, there, second enter. I type it all in again. But why am I getting negative? Okay. I haven't pointed that out. Awesome. And I think it is with, simply had a height of 70 and arm span. So this is 68. Look at me. I think I'm so smart I don't need to practice all these questions and just look at a couple of them and blowing it here. All right, so 68. So we expected 68.6832 and we got 70. So then the residual would be negative. The correlation between the height and the arm span is nope, that's not it. Okay, I just cheated on the last one and put the answer as A. Let's go through and see why the other ones aren't working. I would redo the video, but I'm 23 minutes in and I'm not redoing that. Contrary to Da Vinci speculation, the regression model suggests that these students, at least height is about 84% of the arm span. That's a maybe. For every 1 inch increase in arm span, the regression model predicts about a 0.84 inch increase of height. So for every 1 inch in arm span, then the regression model predicts about a 0.84 increase in the height. Actually, I believe that's right. Maybe I wrote down the last one right. That one seems correct. This one definitely does not seem correct. A student that is 66 inches, the model would predict an arm span of 68 inches. So this one, they're giving us the arm span, which the arm span is the X and the height is the Y. So on this one, if we typed in 68, which I already did, and then we would not get a person that's 66. We would get a person that's 68. So that's wrong. All right. Contrary to Da Vinci speculation, the regression model suggests that for these students, at least, height is about 84% of the arm span. Maybe. Oh, so he said they were the same, and then, well, I'm going to go with D. That's going to be the official answer. And if you watched the video all the way through, you probably got a good laugh here in the last 3 or 4 minutes. I don't see any reason why D is not correct. C is a head scratcher, but I'm going to go with D. Y'all have a good night.